we apply the divergence theorem. So this would be equal to triple integral over E, K, which is a constant, and then we have the divergence of the gradient of T, dV. All right. Well, that is delta squared times T, that is the Laplacian. So Txx plus Tyy plus Tcz. We saw it earlier when we talked about the divergence and curl and all that. So now, what we can say is if I put everything on one side, we have just one triple integral over E, and we have C naught dt dt minus K Laplacian of T. So all of that integrated over the region is equal to 0. Now, by the solid that I've selected is actually arbitrary. So this has to hold over any region you choose, because that conservation energy applies whether you're talking about the entire solid or any portion of a solid. So since this integral over an arbitrary region is equal to 0, the integrand itself must be 0. This whole thing. So we have this equation. C naught dt is equal to K Laplacian of a temperature, and this is called the heat equation. One of the most important partial differential equations in all applied mathematics, something that I've dealt with from time to time in my own research, and all comes from basic conservation principle and various laws such as Fourier's law that relate quantities such as flow rate of heat energy to temperature. So temperature is really what you would be solving for. And there are other equations that also arise from a divergence theorem, such as the wave equation that models wave propagation, for example, that can be derived in a similar way, but also that one involves a second derivative with respect to time. And it's from that Maxwell's equations actually come about that I've also dealt with. So really, it's something that we don't really have any opportunity to talk about here, and it may be a little premature. But next semester you're going to be taking 285, most of you, or practically all of you, I think, on ordinary differential equations. But one of the main uses of those is to set the stage for functions of several variables where you're solving partial differential equations involve partial derivatives. And I believe I have just barely run out of time. So